All right, so let's look at number 1. This one we're going to need to use our calculator for a lot, so make sure you have your calculator. Okay, so we're looking at a region R, and it's shaded, and it's bounded by graphs of natural log of x and x minus 2, as it's shown above. Now, they didn't actually tell you which one is which, but hopefully you'll recognize that this graph, this curved graph, is the natural log of x, and this straight line is the curve, or is the equation x minus 2. All right, so first thing we want to do is find the region, the area of R. So we're going to set up an integral, and we're going to do this, we're going to imagine filling our space with those rectangles, those strips, right, that's touched from top to bottom. Now you could honestly do horizontal strips or vertical strips. I'm just going to fill it with vertical for the sake of, it's a little bit easier for me right now. That tells me they're going to be a dx. Anything I fill vertically is a dx. And then it tells me everything that has to be in terms of x. So the top of every strip touches the equation natural log of x, and that's in terms of x, minus the bottom of every strip touches the equation x minus 2. And the one thing I'm missing here are my bounds. My bounds have to be in terms of x as well. This is where the calculator is going to come in. Normally, we would just set natural log of x equal to x minus 2, and we would solve. However, this is actually really hard to do because, basically, even if we manipulate this, it's going to be pretty hard to solve for an x value, which makes those two equal. So what we're going to do instead is we're going to graph them on our calculator, and I literally put them into y1 and y2 in my calculator. Natural log of x, y2 was x minus 2, and I did zoom standard, and I got to see them both there. All right, so we want to know where they intersect, and so that was second calc, and I did the intersect. And make sure you're actually on a graph, so it says, first curve, second curve, and then it says guess, and I got this point right here. And this point right here had the x coordinate 0.15859434. That was an x value. And right here they intersected. They had the x value 3.1461932. So that's how I got those two intersections. If you need to pause and go and find them, go ahead and do so. But this tells me this is where my my region begins. That's where my region ends, and I'm going to put those as my bounds. 0.15859434 and 3.141932. Now keep in mind, a lot of people are going to look at this and they're going to say, can't we just round everything to 3 decimals? You're allowed to round, that's totally fine, but we really want to round when at the very end of the problem. We want to round our answer. We don't want to round along the way. So if I put this whole thing into my equation, into my calculator, using math number 9, which says FNINT, you're going to put your function, you're going to put all of this, natural log of x minus x minus 2, comma x, comma your lower bound, and then your upper bound. So this is lower, and then upper. Close your parentheses. And if you do that, you should get 1.949, and then a lot of other decimals, but this is where you're allowed to round your answer. You're allowed to just write 3 decimals here. All right, so that's A. Moving on to B. We're going to find the volume of the solid generated when R is rotated around the horizontal line y equals -3. So I'm going to place a horizontal line down here, y equals -3. And if this region is rotated around it, it's going to look something like this. Really rough sketch. So this allows me to confirm that when I rotate it, I'm going to be missing some space. I'm going to have a non-solid solid, which tells me I have a big R and a little r. Okay, so I always want to start at my axis of revolution, which is y equals -3, and draw a line directly up as far as you can go. Now the outside, my big R, is going to be determined by this top curve, this natural log of x curve. My little r will start at the same axis, go up, but it will stop on the inside, which is determined by that x minus 2 curve. So my big R, the top touches natural log of x, and the bottom touches -3. So top minus -3 really becomes natural log of x plus 3. My little r starts at x minus 2, so top minus -3. Once again, that becomes plus 3. So this is really x minus 2 plus 1, so it becomes plus 1. All right, so find the volume. We're going around a horizontal line, so that's a dx. Keep everything in terms of x. My big R is natural log of x plus 3, the quantity squared, minus my little r squared, which is x plus 1 squared. And my bounds are exactly the same as before, from one x value to the other. So that's the 0.1585934, all the way up to 3.1461932. And I'm going to type all that into my calculator. Don't forget your pi up front. When I typed it into my calculator, I got about 10.885, and I multiply that by pi, and that gives me 34.198. I just stop writing as soon as I'm done with 3 decimal places. All right, next question. It says write but do not evaluate. So when they say this, they do not want you to evaluate in the integral. We want the volume of the solid generated when r is rotated around the y-axis. So here's our y-axis. And if this graph was rotated around the y-axis, it would look something like this. Now, as soon as you see this y-axis, that should remind you that's a vertical line. So I need to take everything that was in terms of x, and now we're going to turn it into in terms of y. So my big R and my little r are still required, because if I look here and I draw out, my big R is going to go all the way, and I'm going to have some space missing. That's going to be my little r. So my big R is now right minus left. Now I'm going to do myself a favor really quickly, and I'm going to solve this so that it's in terms of y. This equation was the natural log of x. If I take e of both sides, x is now e to the y. So this curve is e to the y, and the outer curve, that used to be equal y, so now x equals y plus 2. That's what this inner curve looks like. Okay, so big R goes from the line, we just said that was y plus 2, to the axis, right minus left. So y plus 2 minus 0, that's just y plus 2. And my little r goes from this curve, which is e to the y, minus 0, so it's just e to the y. So I have my big R squared, y plus 2 squared, minus my little y squared, e to the y squared. And don't forget your bounds. Your bounds need to be in terms of y's as well. But we know where the x values are where these meet. So what I'm going to do is I'm going to kind of do a little bit of a cheat. Rather than actually plug into my calculator and see what the y values were, I know that this y value down here is going to be the same thing as the natural log of x at this y value. So this y value is actually the natural log of 0.1585934, and the top y value is actually the natural log, sorry, this is bad writing, natural log of 3.1461932. And then since I don't have to even evaluate it, I can definitely leave it like that. All right, last but not least, the base is a 3D solid, and the cross sections, and I should say where they're perpendicular to. So I'm going to say perpendicular to x axis. Our squares, find the volume. So this was where we talked about this is a square coming out. There's tons of squares coming out. And all we have to do is integrate the area, right? dx. Well, the area of a square is side squared. Well, what's each side? The side goes from this top to the bottom, which is natural log of x minus 2. Okay, so if I integrate the area, I'm going to integrate natural log of x minus x and minus -2 becomes +2. dx, same bounds as before, 0.15, 859,434, all the way up to 3.1461,932. All right, and we're done.